Hello, in this unit, we are going to explore electronic structure of atoms. Electron structure of atoms is also called electron configurations. The energy of atomic orbital increases as the principal quantum number n increases. As we know, the principal quantum number, the symbol is n. The allowed value is 1, 2, 3, 4. The physical meaning is shell, the general region for the value of energies for an electron in the orbital. As the principal quantum number n increased, the size of orbital increases, and the electrons spend more time farther from the nucleus. Thus, the attraction to the nucleus is weaker, and the energy associated with the orbital is higher. This means less stabilized. Orbital energy and atomic structure. In any atoms with two or more electrons, the repulsion between the electron makes energy of subcell with different value of the L differ. What is subcell? What's L? As we know, the L is the angular momentum quantum number. Allowed value is from 0 to n-1. The physical meaning is a subcell, the shape of the orbital. The energy of the orbitals increase within a shell in the order of SPDF, S less than P, less than D, and less than F. Electrons in atoms tend to fill low energy orbital first. Here, showing you SPDF, the shape of this orbital. This is the generalized energy level diagram for atomic orbital in an atom with two or more electrons, but not to scale. As you can see, it's 1s, 2s, 2p, 3s, 3p, then 4s, then 3d, then 4p. Electron configuration. The arrangement of electrons in the orbital of an atom is called the electron configuration of the atom. An electron configuration consists of symbols that contain three pieces of information. The principal quantum shell, N. The later they designated the orbital type, L. A superscript number that designates the number of electrons in that particular subcell. Here is an example. The diagram of electron configuration specifies the subcell NL value with the letter symbol and the superscript number of electrons. Here, this one is the principal quantum number. The S is subcell, and the superscript is the number of electrons in the subcell. The Opal principle. To determine the electron configuration for atom, we add a number of electrons equal to its atomic number. Beginning with hydrogen and continuing across the period of the periodic table, we add one electron to the subcell of the lowest available energy. This procedure is called the Opal principle, from German word Opal, to build up. When writing electron configuration and orbital diagrams, keep in mind the Pauli exclusion principle. This diagram here depicts the energy order for atomic orbital and is used for deriving ground state electron configuration. How to draw this diagram? The first is 1s1, 2s2p, 3s3p, 3d, 3s3p, 3d, 4s4p, 4d, 4f, and 5s, 5p, 5df, etc. And then draw the line this way. Start from 1s, 2s, 2p, 2p, 3s, 3p, 4s, and this is the energy order for atomic orbital. This figure showing you the this is the periodical table shows the electron configuration for each subcell by building out from hydrogen. This table can be used to determine the electron configuration for any atom on periodic table. Okay, as you can see, here is the electron configuration. Okay, and showing here is 1s, 2s, 3s, 5s, and here 2p, 3p, 4p, 5p, 6p. Here transition element 3d, 4d, 5d, 6d, and the inner transition element f, 4f, and 5f. Configurations and the orbital diagram. What is the orbital diagram? It looks like this. Orbital diagrams are pictorial representations of the electron configurations, showing the individual orbitals and the pairing arrangement of the electron like this. This is the electron configuration, the orbital here, individual orbital, and this is the pairing arrangement of electron. And here, an upward arrow represents an electron with the spin quantum number at ms positive 1/2. And downward arrow is not shown here, represent an electron with spin quantum number ms equal to -1/2. Here are some more example. The helium, the atomic number is 2. There are 2 electrons here, and lithium 3 electrons here. Barium is 4 electrons here. Boron here have 5 electrons here, and here is following the Hund's rule. What is Hund's rule? Hund's rule is the lowest energy configuration for an atom with electrons within a set of the degeneration orbital is that having the maximum number of unpaired electrons. So it's, for example, here from boron to carbon, instead of put the electron here, put the electron here, and put your unpaired first. Maximum number of unpaired electron. Here 2 unpaired electron. So the atomic number increase from nitrogen to neon. The 1 more electron put here, and then the more electron will put here. So these are following the Hunter's rule. I found the reference of this OpenText written by Flowers, etc., and it's licensed under the Creative Commons Attribution License version 4. Thanks.